So in this video I leave here some properties of permutations. The very first theorem is about products of disjoint cycles. Every permutation can be written as a cycle or as a product of disjoint cycles. I think I wrote this example in some previous video. So this is the beta is 1, 2, 3, 4, 5, 6, and the beta permutation is 1 goes to 5, 2 goes to 3, 3 goes to 1, 4 goes to 6, 5 goes to 2, and 6 goes to 4. So we can write beta in cyclic notation. So 2 goes to 3, 3 goes to 1, 1 goes to 5. So 2, 3, 1, 5. Okay, and then 6 goes to 4 and 4 goes to 6. So we write 6, 4. So here the permutation is written in a cyclic form. Okay, and what this theorem says is that every permutation, like this one, can be written as a cycle or as a product, like this one, as a product of disjoint cycles. The proof is really easy. I'm not going to do it. A second property of permutation is this one, theorem: disjoint cycles commute. If the pair of cycles alpha for alpha A1, A2, AN, and beta B1, B2, Bn. If the pair of these two cycles have no entries in common, then, since they are disjoint cycles, they commute, meaning alpha times beta equals beta times alpha. The proof is really easy, and I'm not going to do it too. An important corollary. They say this one is due to Ruffini from 1799. I'm not sure about this. The order of a permutation. The order of a permutation, written in disjoint cycle form, is the least common multiple of the length of the cycles. I'm not going to do the proof here. I just want to call your attention for permutations if the cycle is of length 2. Okay, so this will be something like this, AB. Some authors, they call this sort of permutations, they call it transpositions, because AB interchange or transpose A to B and B to A. Okay. One way to write this in this transposition 1, 2, 3, 4, 5. We can write this as 1 goes to 2, 2 goes to 1, so 1 goes to 3. Okay, 1 goes to 2, and 2 to 3, so 1, 2, 1, 3, 1, 4, 1, 5. There are many ways to write this. We can write, so 1, 5 goes to 1, 1, 5. We can write this as 1, 5. Then it would be 2, 5, right? 3, 5, 4, 5. Another way could be 2 goes to 3, 2, 3, 2, 4, 2, 5, 2, 1. Another way, 1, 3, 2, 3, 2, 5, 2, 1, 5, 2, and 5, 4. I gave this example to show that these two cycles, the number of two cycles may vary from one decomposition to the other. You see, here we have 1, 2, 3, 4, and here we have 1, 2, 3, 4, 5, 6. Okay, so decomposing in two cycles may vary from one decomposition to the next one. Okay, but some aspects of decomposition will stay the same, but I'll speak about that. A quick lemma is if eta equals beta 1, beta 2, beta r, where these betas are two cycles, then r, the number of two cycles, is even. And there is a beautiful proof for this, but I'm not going to do it. Theorem: always even or always odd. If a permutation alpha can be expressed as a product of an even number of two cycles, then every decomposition of alpha into a product of two cycles must have an even number of two cycles. So imagine alpha is a product of beta 1, beta 2, beta r. All these betas are two cycles. Okay, all these betas are two cycles, and it can also be expressed as gamma 1, gamma 2, gamma n, and these gammas, they're also two cycles. Then r and I call this n, right? N, r and n are both even or both odd. So if you make a decomposition and r is even, any other decomposition will be even too. If you make a decomposition and that is odd, any other decomposition will be odd too. Okay, another definition: even and odd permutations. A permutation that can be expressed as a product of an even number of two cycles is called an even permutation, and a permutation that can be expressed as a product of an odd number of two cycles is called an odd permutation. So that's an odd permutation or an even permutation. A quick and very simple theorem: even permutations form a group. The set of even permutations in SN, the symmetrical group of order n, forms a subgroup of SN. So what are the even permutations? Well, the group of even permutations usually is denoted alternating group. Okay, so this will be a subgroup of the symmetric group. Okay, so the group of even permutations with n symbols is denoted an and is called alternating group. Well, alternating, the complete wording should be alternating group of order n. The alternating groups are very important. We are going to see very important alternating groups like A4 and A5. This is a decisive group that we will see many times to appear. It's obvious that the if we pick the SCN, only half of the SCN will be AN. Okay, half of the members of the symmetric N group are even permutations. The alternating group A4, the root of this group, describes the rotations of a tetrahedron. The 12 rotations of a regular tetrahedron can be described with the elements of this alternating group 4. Okay, I'm going to more or less try to draw it. So the very first one will be 1, the identity. So the edges are A, B, C, D, and the numbers are 1, 2, 3, 4. Okay, so now we will have a rotation on this axis. So B and A will exchange. So A will be here now and B will be here. And D was here and C was here. So now we'll have C here and D here. Right, so we had this rotation through this axis. Okay, so 1 goes to 2, 1 goes to 2, and 2 goes to 1. 1 goes to 2, 1 goes to 2, and 2 goes to 1. 3 goes to 4, so 3 goes to 4, and 4 goes to 3, and 4 goes to 3. Okay, so this A is now B, these two exchanged, and these two exchanged. So next one will be 1 to 3 and 2 to 4. Do not forget we are in the alternating group. Okay, so 1 is A. A goes to 3, so now A will be here, and 3 goes to 1. So what was here? C was here, right? So C will be here now, because we have a rotation through this axis here. So C goes to A. Now 2 goes to 4. So B goes to D. Right? Here we had B. Okay, and now we will have D, and here B. 1 went to 3, here you are, A went to 3, and 3 went to A, so C and went there. Okay, we had a rotation through this axis. Now 1 goes to 4, so we have a a rotation through this same axis here. We have a rotation through this axis, but this time the rotation will be, this one was through this point and this point, and this one is through this point and this point here. Okay, so there will be still this movement. Okay, so 1 goes to 4 and 4 goes to 1. Okay, so 4 goes to 1, this will be D, this will be A, 2 goes to 3 and 3 goes to 2. So B and C, they exchange, so we have C and B now. Okay, now the rotation will be through this axis in this direction. Okay, 1 goes to 2 and 2 goes to 3. So that will be, this one will be A, B and C. So nothing is said about 4, so 4 stays the same, right? So this will be D. Oh, this should be wait a sec, this should be through this point here. Okay, so this is correct, but through this point here. Okay, because D stays the same. So 4, 1 goes to 2, 2 goes to 3, 3 goes to 1, so D stays the same. Okay, so the rotation will be through this axis here. Okay, and through this point here. Okay, 1 went to 2, A and went to this position, 2 went to 3, so B went to this position, and 2 goes to 3, right? So C moves on. Okay. So now we will have a rotation through this axis here, right? So 1 goes to 3, 3 goes to 4, 2 stays the same. Okay, so B doesn't move here. Okay, and we have, so 1 goes to 3, 3 goes to 4, so, and 4 goes to 1, so D moves here, right? 1, so A goes to 3, A goes here, and C goes here, right? I think that's okay. Okay. So now we have 2 goes to 3 and 3 goes to 4, right? So 1 stays the same, so it's a rotation around this point and this axis in this direction. So 2 goes to 3, so we have 2 was C, right? 2 goes to 4 and 4 goes to 3, right? Yes, 2 goes to 4 and 4 goes to 3. That's the correct position. Okay, so 2 goes to 4, so we'll have B here. B goes to 4, B will be here. A stays the same because 1 goes to 1, and there will be C and D here. Okay, do not forget we are in the alternating group. Okay, A4. Okay, now 3 stays the same, so 3 goes to 3, and 1 goes to 4, 4 goes to 2. Okay, that will be the rotation around this axis here. So C stays in 3, right? So this one will be D, because 1 goes to 4, 4 goes to 2, 2 goes to 1, right? This will be B, and this will be A. Okay, now rotations around this axis centered in 4, so 4 stays the same. 1 goes to 3, 3 goes to 2, 2 goes to 1. So A, B, C, and 4 stays the same, so D stays the same. Okay, rotation in this direction around this axis, 1 stays the same. So the cycle is 2 goes to 3, 3 goes to 4, 4 goes to 2. So 1 stays the same, that will be A, and here there will be D, right, B, and C. So 1 goes to 2, 2 goes to 4, so 3 stays the same, and we will have a rotation around this axis. Okay, so 1 goes to 2, 2 goes to 4, 4 goes to 1, so this will be A. C stays the same, right? D, and this will be B. A, B, D, right? 1 goes to 2, 2, B goes to 4, and 4 goes to 1. Okay, rotation around this axis. And the last rotation will be 1 goes to 4, 4 goes to 3, so it's around point 2. So this stays the same, that's B. So 1 goes to 4, so this will be D, B, and C. 1 goes to 4, 4 goes to 3, 3 goes to 1. So we just show the 12 rotations of a regular tetrahedron given by the alternating group 4. Okay, so we had rotations of a tetrahedron. This was the original tetrahedron. First one stays the same, so that's the identity. Cycles 1, 2, 3, 4. So this was the identity. Second cycle, third rotation, second cycle, no, second rotation, third rotation. Okay, 4, 5, 6, 7, 8, 9, 10, 11, and 12th rotation.